All right, let's look at the constant expression problem. This is for loops. So let's read the question. The following pseudocode performs a key search on a sorted linked list. The content of the list and the fact that the list is sorted are known to the attacker. The attacker wants to infer secret value of the sorted key, of the key by figuring out how long the code runs. And then there are two parts of the problem. First is transform the code so that the number of loop iterations is independent of the secret, but you may have a secret dependent conditional branch. And part B, transform the code to eliminate all secret dependent behavior. Okay, so let's take a look at this code right here. So we have a key that is a secret, and then we have a function called key found that takes in the key, and what it does is that it traverses a linked list. So it starts with the pointer P with the head of the list, and then a loop that says while P is not null, so while is not the end of the list, and while the key is not found, so you keep advancing the pointer until one of these is true. If the list reaches the end, so that will be null. So then here we will return false, meaning that the key is not found. But if the key is the same with a key in a node, then we also quit the loop, and that will go to the else state and then return true. Okay, which means that if the key is found, the number of iterations of the loop is determined by where the key is found. So if the key is found right away, then it will run for a few iterations. But if the key is found very late, it will run for more iterations. And if the key is not found, it will run the entire, the maximum amount of time because it traverses the entire linked list. Okay, so obviously because of this, then the amount of time the loop executes determined by the secret key, which is the problem, right? So in part A, we have to transform the code so that the number of loop iterations it becomes independent of the secret. Okay? So the main issue here is that we have the termination of the loop depending on the key. So it's this part right here. So we have to remove that. Okay. Now what we can do is basically then to find um, or to record the fact that the key matches, but without quitting the loop. Okay. So in order to do that, we will rewrite the code this way. So this remains the same. The declaration remains the same. Now the loop, we're going to change it. Okay, so instead of quitting early, if we found the key, we are not going to do that. We are going to continue traversing until the end of the linked list, right? So here we will use a new variable here just to record the outcome. Sorry, it should not be here. It should be earlier here. So we're gonna add a variable. And we're gonna initialize it to false. So here we're going to use that variable whenever we find a match. So here basically if p key equals to key, Remember earlier, we quit the loop when we find that, but here we don't quit the loop. We just record that we found a match. So we assign outcome the value of true. Oops. And then we advance the pointer. So that closes the new loop. And the rest is the same. I mean, we can, but we have to change what we return. So in this case, we return the outcome. Okay, notice that the outcome was initialized to false. So if there is no match, so what we return will be false. If there is a match, our outcome will be true, and that will what we will return. Okay, so that finishes the first part. We no longer have loop termination depending on secret. However, we still have we have a conditional branch that depends on the secret, which basically is a source of side channel. So we have transformed one source of side channel to another. So in part B, we are asked to eliminate this, right? How can we eliminate the secret dependent branch? So in order to do that, see, let's just use this side. In order to do that, we just going to accumulate or transform into a logic expression, right? So of course you can use the Carnot map, this and that, but this is very simple problem, so we don't have to. So all we need to do is just to uh, to use a simple logic. So this is part B, secret key, and then we still have the same declaration. We carry over the declaration of outcome and initialize to false as the same as before. But here we are going to use another one. The comparison result. We are going to accumulate to this result. We can initialize it to false, or we don't have to initialize it. Okay. So next, pointer P, we initialize it to while P is not null. So far it's the same as before. The exception is that we add CMP result. So here, instead of an if statement, we compute whether there is a match or not by converting the following comparison. So this is now an arithmetic. This is arithmetic. So if they are equal, they will be subtracted out and it will be 0. And after it becomes 0, then we convert it to Boolean and then invert it so that if they are equal, we will have a 1. Okay? And vice versa. So that's the compare result. So then once we have the comparison result, which is now no longer using an if, now we can accumulate it into the outcome. And to accumulate, because the outcome should be true if we have just one match, right? So then we will use an or comparison result. With an or, if the comparison result is false, we retain the old value of outcome, no change. But if the comparison result is true, then it will be carried over into outcome. It will be retained, basically. And then after that, we just advance the pointer. And then close the loop, and then we return outcome. And then close the function. Okay, here basically we no longer have a conditional branch. This is all logic operation and arithmetic. Okay, so therefore here we no longer have secret dependent loop termination. We no longer have secret dependent conditional branch.